I would like to thank the organizers for inviting me. It's a great pleasure to be here in India. So I'm going to talk about Hausdorff dimension in a non-conformal setting. I will explain in a minute what non-conformal means, which is the issue here. So the examples we should have in mind, the simplest ones, are these Lally-Gatzouras carpets. So this is an iterated function system. So it's a collection of transformations. Here it's from the unit circle, okay, into itself. So these rectangles here are the images of one of those transformations, okay? So we have a collection of transformations from the unit circle onto itself, and these are the images. Okay, so the main restriction here is that these rectangles are aligned in horizontal rows, okay? And the other one is that the images are disjoint. So this alignment in horizontal rows means that we'll have a dynamics here on the vertical space, okay? So we can call this vertical space the space of the fibers, horizontal fibers. Okay, so what is our fractal set? You continue to iterate this thing. What does this mean? In each of these rectangles, okay, you put an affine copy of the whole picture, okay? So in here, it will be like the initial figure, but scaled to here, okay? So there will be a bunch of holes here, okay? And we do that in each of these rectangles, okay? So these rectangles have widths, the Aij, that I've written here in red, okay? These are the widths of the rectangle, and the heights are these Bi's, okay? So I here.
So you're not scaling the same scaling?
No, the scaling is according to these numbers, okay? So these here will be bigger here. If you zoom this to the whole unit square, you obtain the same thing, okay? So the zooming is according to the inverse transformation, okay, corresponding to each rectangle. So another property that we will use is this domination condition here, okay, which says that the widths are less than the heights, okay? And this corresponds exactly to what I've said, non-conformal. So there will be here two rates of contraction, okay? And this says that the contraction is bigger on the horizontal than the vertical, okay? So this is a domination condition. So what did Lally-Gatzouras carpets did? So here is the Hausdorff dimension of the fractal set when you iterate this over and over and over again, okay? In the limit, we will get this attractor lambda, okay, which is a fractal set. And so they computed the Hausdorff dimension according to this formula here, okay? It's not so easy to obtain because exactly of the non-conformal. So these rectangles, when we iterate, in the next step will be very distorted, are not approximately balls, okay? So what does this formula mean? So it is saying that it's the supremum of these Piagets, which corresponds to Bernoulli measures over these dynamics, okay? And this expression in brackets here is just the Hausdorff dimension of the Bernoulli measure corresponding to this Piaget. Piaget is a weight on these rectangles here, okay? And what does it read? It's a sum of two numbers. The first number is very natural in the Hausdorff dimension, okay? So it corresponds to the dimension of the measure on the vertical space, okay? When we project the measure onto the vertical space, and it is entropy over the projected measure. Pi is the projected measure of the Pij's, and over the corresponding Lyapunov exponent, okay? It's given by these contractions here, Bi's, okay? So this is entropy over Lyapunov exponents on the vertical. This is very well known for conformal dynamics, okay? In vertical, we have a conformal dynamics, okay? Plus now another similar expression for this, but now for the dimension of the fibers, okay? When we iterate this, there will be a lot of fibers, of course, okay? So, and this is the dimension of a fiber with respect to this measure. This is the relative entropy, okay? This is the whole entropy of the space minus the vertical, gives like an entropy in the horizontal direction over the corresponding Lyapunov exponent on the horizontal fiber, okay? And this formula saying that the variational principle for dimension holds. So we can obtain the Hausdorff dimension of the attractor as the supremum over Bernoulli measures supported on the attractor, okay? And it's clear that since this is a compact space of Pij's, this is a continuous function, that there will be a measure of full dimension, okay? So what we start doing is generalize this to nonlinear Lally-Gatzouras carpets, okay? Which are, as before, defined by an iterated function system, which is a collection of functions defined on a unit square, but now they are not linear. They possess this Q product formula, which says that we have a projective dynamics on the vertical space as before, okay? So in other words, these transformations preserve horizontal lines. That is the main restriction here. And so, as before, the images of this over the unit square are distorted rectangles now, and we assume that they are disjoint also, okay? And now the combination condition reads as this, okay? So in the x direction, which is horizontal, the contraction is bigger than in the vertical direction. So you can also speak in terms of dynamical systems, okay? Now, if you speak in dynamical system language, then this will be an expanding dynamical system, okay, with the same Q product formula. And the inverse branches of it are exactly these transformations, okay? So I will speak mainly in the dynamical systems language. So in other words, this F transforms each basic rectangle, which is something like this, okay, but now are distorted, onto the unit square. So now we can speak of expansions. So and we have the analog variational principle here. So here is the entropy of a measure, okay, projected in the vertical space, okay, B, over its corresponding Lyapunov exponent. Here is the other dimension of the fibers. This is the relative entropy and the corresponding Lyapunov exponent in the horizontal direction, okay? And this is the dimension of an ergodic measure, okay, supported on that attractor. If you make the supremum of this, we recover the dimension of the attractor or repeller now. Okay?
This last fact that you said, is that a standard thing or is that non-trivial?
What?
The fact that it's this, somehow you get the house of dimensions.
No, it's not. It's highly non-trivial because actually in higher dimension, here we are talking 2 dimensions. Yeah. In third dimension, it does not hold at all.
So in 2 dimensions, can you say for a given measure, what does that number give you? What
This,
information?
it's the dimension of the measure.
That is the dimension
Yes.
of the measure, which means basically the local dimensions.
Yes, you can speak of that, the local dimensions, okay?
And why is the house of dimension given by the supreme one?
No, the other dimension is another definition, is the classical definition,
I know,
okay?
I know. So how come you have that equality? So that's your theorem.
Yeah, that's a theorem, okay? It's not, it's given the previous one by Lally-Gatzouras. This is the main theorem, okay? You use bounded distortion and stuff. Of course, some of this stuff here are not very easy to transport to nonlinear. So I have to make several adaptations and prove things a little different, okay? So it's a generalization of this theorem here, okay, to the nonlinear setting. So a main difference is now, instead of Bernoulli measures, you have to take the whole space of ergodic measures. So since, and this formula for the dimension of the measure only holds for ergodic ones. So it's not trivial that there is an ergodic measure of full dimensions. In other words, that this supremum is attained with an ergodic measure, because the set of ergodic measures is not closed, okay? So that is a natural question, okay, which is not trivial too. So to answer that question and others things about this respect, we introduce a general thermodynamic formalism for dimension, okay? So we consider a subshift, okay, which will represent the whole dynamics in the two dimensions, and a factor map, okay, which will represent the vertical dynamics in the previous examples, okay, which is a mixing subshift of finite type. It's not so well important. It's because we want, this is a condition typical in dynamical systems, in thermodynamic formalism, but it can be relaxed, okay? It's not so important there. And we'll call P the factor map. In previous examples was the projection onto the vertical space, okay? And we will consider this whole system, okay? Fiber-wise expanding. I will not explain this in detail, but as the name suggests, it's expanding on fibers, okay? So this is the setting, fiber-wise expanding, of the relativized variational principle by Denker, Gordon, and Heinemann, which says the following. If you fix a measure on the vertical space, so S here is the vertical space, okay, and there are other continuous potential in the whole space, then you have this variational principle. So you make the supremum over invariant measures that projects onto this fixed new measure. You make the supremum over the relativized entropy plus integral of the potential, and this will be equal to an integral over nu of a function here, okay, which depends on that potential, that is older continuous, okay? So this is not the usual relativized pressure, okay? The relativized pressure is only measurable, and this will be important, okay? So to differentiate it from the relativized pressure in the relativized variation principle by Walters, for instance, we call it a gauge function, okay? So it is important to be order continuous. So they also prove that there is a unique relative equilibrium state, which means that this supremum is attained at unique measure, okay, with respect to this measure and phi potential, okay? And the mu is ergodic if nu is ergodic. So this will be the main tool that we'll use, okay? So fix two potentials, okay? One in the vertical space and the other one in the whole space, which has positive and older continuous, okay? This will make the role of the Lyapunov exponents, okay? So for a measure in the whole space, you define this quantity here, which we have seen before, okay? If mu is an ergodic measure, you can interpret this expression here as its dimension, the dimension of the measure, okay, as before. So, and you consider the supremum of this quantity over all invariant measures, which we call D, okay? This D might be interpreted as the Hausdorff dimension of the repeller, okay? When the variational principle for dimension holds, as in the nonlinear Lally-Gatzouras carpets. So, and we say that mu is a measure of maximal dimension if the supremum here is attained at that measure, okay? So, it is easy to see that this D here, this supremum, can be written in this form here, okay? So, this first expression is exactly the same as before, as this one here, okay? We are calling the projected measure nu. We are fixing such a measure nu. And then if we fixing this projective measure nu, if you make the supremum of this second quantity over mu that projects onto nu, you get exactly this number T nu. It's the definition of it, okay? First we fix a measure nu, maximize the second term over all mu's that project onto nu, okay? We get this, and this is the other expression. Why we are doing this? Because now we are going to the vertical space. We are trying to reduce this problem to a problem in the vertical space, okay? To a one-dimensional problem, let us say like that. So this T nu can also be given as the root of this equation here. So this T, if you put here, multiplied by the potential on this gauge function, there is a unique T that zeros this, okay? So this might be interpreted as a random Bowen's equation, okay? That gives the Hausdorff dimension of a typical fiber, horizontal fiber, okay? With respect to the measure nu. Okay, it's a random, it's like a random conformal case, okay, in the fibers. So as we say, we are doing this because we are trying to reduce to the classical variation principle in the vertical space. So let us consider a parameter T, okay, that runs through the values of this function here, which is the all possible dimension of the fibers, okay? Then we define this potential. Yeah. That's where I'm trying to get, okay? It's not trivial, because this is not a constant, it's not linear in the new. That's where I'm getting it, okay? That's the main thing stuff. That's why we are going to fix this as a T, as a parameter, okay? And then we are trying to reduce to the classical variational principle. If we define this older potential here, it looks strange, but it's not so strange like that. This first term here is the usual one in the conformal case, okay, here. Then we add this new term, okay, which depends on the gauge function, okay? So remember that now we are in a vertical space now. This is older potential because this gauge function is older, okay? I will explain now what this beta T is. It's not so important. Let nu of this potential be the classical Gibbs measure with respect to this potential, okay? That is the classical thermodynamic formalism, okay? Then beta T is a normalizing constant, so that the dimension of the fibers relative to this potential, to this measure here, is exactly the parameter T. Okay, so this parameter T here has always the interpretation of an horizontal dimension, okay? Otherwise, it wouldn't be relevant. And finally, consider the measure mu, okay, on the whole space that is the relative equilibrium measure with respect to this measure, mu, and this potential minus 2 phi. So we have this theorem here, okay, that classifies the measures of maximal dimension. It says that a measure is of maximal dimension if and only if is of this form here, okay, and the parameter t is a solution of this equation here with respect to this potential, okay. This is the classical pressure function on the space Ys, okay, for some t, okay. So in that sense, this is the title. It's a generalization of the classical Bowen's equation for conformal case, okay. And also 0 is the maximum value of this function, so there is at least one measure of maximal dimension. But now the main difference with respect to the conformal case is that there might be several solutions of this equation here, okay? Which means that there might be several measures of maximal dimension. Okay, thank you very much.